Good morning, students. So today we are going to complete rotational motion, right? Okay. So what we saw yesterday, where we stopped? We were stopped at angular momentum and we discussed about torque. Okay. So we are starting with the torque only. On torque, what we want? We'll see a few problems today. Okay. Torque was what? We said torque is R cross F. Very similar to angular momentum. Angular momentum was R cross P. This is R cross F. In angular momentum, we did one question on projectile. Okay. Same question we can do here also. We'll try. Okay. So this is projectile. This is velocity of projection. This is angle of projection. And suppose now I want to know the torque of this projectile when it is at the highest point. Okay. When the particle is at highest point and when the particle is about to strike the ground. So if suppose this point is P here and this point is Q and this point is O. So we want torque of which force? Gravitation only is only force acting on this one. Okay. So torque of gravitation force at point P. So torque at P about O. This is what we want. And torque of Q about O. And these two things we want. This is the projectile, projection speed u, angle of projection theta. When it is at height P, what is the torque of gravitation force about O? And when it is at Q, what is the torque of gravitation force about O? Very simple. This is highest point we know, right? And mg is acting downwards. We know that. So torque is R cross F. That means you should be searching perpendicular distance. Okay. What perpendicular distance? Perpendicular from the direction of force. This is force. In between this and point of projection, what is the perpendicular distance? This is perpendicular distance. How much is this? This is range by 2. The torque, mg, r by 2. That's all. Okay. Mg into r by 2. We'll write over here. Directly? Yes. Do we have to worry about direction? No, we don't have to be worried about direction over here. Reason, we can directly find it with our right hand. How? R cross F only, no? This is R. Okay, so R actually means what? R is this. This is actually R. Okay, so put your hand in the direction of R, curl it in the direction of force and see where is the direction inside. Okay, clockwise sense is the rotation. So inside is the torque. No issues. This is the magnitude. But what this is not radius, this is range. So we'll write its value. Mg into range is what? U square sine 2 theta by g. This is range. By 2. Okay. So g you can cancel. That is the torque. Now what about this one? When it is about to strike the ground Q, here also mg is acting like this. So mg is like this and perpendicular distance of this direction of force from point of projection is what? This range. So then mg into r, that's all. Mg r. So mg into u square sine 2 theta by g. G is getting cancelled. This is torque of this projectile motion about highest point, when it is at highest point and when it is about to strike the ground. Okay, very simple. Right. Let's do one more. Now this time, let's take one rod. Okay, suppose rod is here. This is the rod. Kept horizontally. Now, we are allowing it to move down. We have made it fixed over here. It's like this. It's hinged, not fixed actually. It's hinged. Okay, its length is L and mass is M. Okay, so what now? We are allowing it to move down. So suppose it came down, right? So it came down Okay, fine, try. Okay, now came down. Can it rotate? No, I don't think so. I don't think so. So better is make one more. Hmm. Okay, we'll make one more to show that. Oh, initially one is went where? My God. Okay, right. So here we'll make one more. But how to make it turn? I don't think it's possible. So I'll make it with my hands only. Okay, let's make it. So our rod now is like this. This way. Okay, came down by theta. This is theta. Now in this position, what is the torque of gravitation force? About hinge point. Hinge point is O. Okay, find torque of gravitation force in two positions of rod. Gravitation force about O in two positions of rod. Two positions of rod. Okay, now first position, let's see. First position, we know mg is acting where? Mg will be at its center of mass. Here, this is mg. Okay, first position. So torque will be what in first position? Very simple. This is mg. This is L by 2. So torque value is mg L by 2. No problem. Second, now second one, mg is acting here. Okay, this is L by 2. Now the question is this L by 2 perpendicular to mg? Answer is no. Then what is perpendicular? Perpendicular is this. This distance is perpendicular. This is perpendicular. So I require this, not this. Here L by 2 was perpendicular, I wrote mg L by 2. But here, this L by 2 is not perpendicular. I require this. From point of suspension, what is the perpendicular distance at which force is acting? That is only R. So what is this now? Let's make this triangle. This is L by 2, I know. So do we know this angle? Yes, this is only theta. Theta, this is also theta. So what is this? This is L by 2 cos theta. That's all. So what is the answer? Mg L by 2 cos theta. Finished. Finished. Okay. Clear? Okay. Let's see few questions on equilibrium also. Okay. Equilibrium means what equilibrium? So far we have seen equilibrium in laws of motion where total force was zero. But in rotational equilibrium, when we say equilibrium, we require translation equilibrium as well as rotational equilibrium. That means total force also zero, total torque also zero. Okay, so based on this also sometimes questions are asked. The first thing is what is equilibrium here? This is sigma of force is zero. That means this is translation equilibrium. Translation equilibrium. Okay, then sigma of torque is zero. This is rotational equilibrium. Right. So, any question is there? Okay, let's see the question. Let's see the question. All right, one more rod we are taking. Is this a rod? Okay. Like this. And on this one, let's assume here is support and here is also a support. And mass, okay, length also. Length we will take is 1 meter. Mass of this rod, M. The M we will say is, let's assume it is 8 kg. Okay. And we are having one more load over here, like this. You suspended, small load. What is that? 2 kg. Where we have suspended from here, let's say 40 centimeters. Okay. A question asks us, if it's in equilibrium, find normal reaction of these two supports. If the rod is in equilibrium, find the support of these reactions. Okay. Find reaction support if rod is in equilibrium. Okay, you say fine. Let's see. Let's make the free body diagram fully. Mass is 8 kg. That means the weight of this rod is also there. Where is the weight? The center. How much it is? 8 kg. So 8 G is acting here. Here 2 G is acting. Okay, and since we are saying it's in equilibrium, that means translation equilibrium is also there. So translation equilibrium means is sum of all the forces should be equal to 0. So suppose that this is N1 or NA, we will say. This point is A. It will say reaction of this one on the rod is upwards, that's NA. Okay. And this one is B. So here reaction is NB. Right. So for total force to be 0, upward force must be equal to downward forces. So NA plus NB must be equal to what? 8G plus 2G, 10G. Okay. NA plus NB is 10G, we know. But what is NA and what is NB? For that, what we have to do? We have to go for other thing. What is that? Rotational equilibrium. Here what we did? Translation equilibrium we applied. Now we are going to apply rotational equilibrium. Now, sigma of torque should be 0. About which point? Any point you take. Normally, we take either A point or center or B point. From there only, we try to find the values. So what we will do? Let's take NB, or not NB, B point. We are going to say torque about B is 0. Okay. So I am putting B here. Now, what are the forces which are applying the torque at point B? 8G is applying, 2G is applying, and NA is applying. How are they applying? These two are applying torque so that it can go down. These 2 points can go down. That means how it is? Suppose this is pen. Okay. These two forces are applying force downwards. So this should be going where? Down. And this NA is applying the torque upwards so that it can go up. Then only the net torque will be 0, no? This will give anti-clockwise torque, this will give clockwise torque, or this will give anti-clockwise, this will give clockwise. Then only the net torque will be 0, right? Okay. So now, torque of these two, which are trying to pull the rod downwards, must be equal to the torque of this NA, because this is trying to take rod upwards. That's what I am going to do over there. Okay, so see now, torque of this 8G into this distance. Perpendicular distance is this. How much is this? Half a meter. Okay, so see, 8G into 0.5 plus 2G. Now 2G is how much? From here it is, this is 40 centimeter, so this will be 60 centimeter. Okay, so 2G into 0.6. 2G into 0.6 equal to, directly equal to, because this is producing a torque which is anti-clockwise, and this is going to produce torque clockwise. So I am writing it other side of equal. So Na into what? 1 meter. Hg into 0.5, that means 4g. 2g into 0.6 means 1.2g equal to Na. So directly Na I got, Na is 5.2g. We wanted Na, we got it. Nb, this value I am going to put it in this one. So Nb value is what? 4.8g. That's it. Yes, it's over. Okay, so equilibrium questions we can do like this. These kinds of questions are also asked at times. Sometimes ladder question will come. That also I'll show you. Okay. So how it is? Okay. Right. So this is the support. Ladder question actually becomes slightly lengthy. Okay. So ladder. Okay. Then this is our ladder. Okay. This is ladder. Ladder's length will be L. Ladder's length will be L. Okay. This is the length and this is equal to L. Mass is M. Okay. Mass is M. Then what type of question they can ask? They can ask you that what are the reactions of the wall? This is wall. Okay. This is wall here. So what reaction wall can give to the ladder? And they can put one man also on this one. That is also possible. Friction also they can keep. So it depends. Like if you want to make more lengthy, you can make it more lengthy also. Okay. So here, let's say this is point A and this is point B. So here reaction is like this, is Na, and here is reaction Nb. Okay. Now what else? Mg is acting in the middle. Okay. If you want to put any load on this one, that also we can do. Okay. Suppose you want to put something over here, we can say okay, 1G is acting here. Right. Now we can make this as rough. So this is rough, there will be friction here. So what will happen actually? This one, which is, this is your ladder, okay. This is our ladder. So this ladder is likely to slide in this direction because this has to come down. Natural movement of this is downwards like this. And this one, so here friction will be acting in this way, like this. If you want here also friction we can add, but normally this will be given, this will be kept as smooth. So I am keeping smooth, like this. So I am just framing the equation, okay, we are not finding anything, I am just framing the equation, just see that how to do that. So first is sigma f should be 0. Right. Now in this case, you can see vertical forces are also there, horizontal forces are also there. So we will be doing sigma fx separately, sigma fx to be 0 and sigma fy to be 0. Okay. So sigma fx means what? You can see that Na is acting towards left and friction force is acting towards right. That's it. There are no more horizontal forces. So directly we can write Na is equal to force of friction. Na equal to force of friction. This is our first equation. Fy, let's see. Fy, what is there? Nb is acting upwards, 1g and mg. Both are acting downwards. So we'll say Nb equal to m plus 1g. Now friction force, what we will take? If it started sliding, no. We have to stop it. Okay, and we have to write, this should not slide at all. That means you have to write maximum force, maximum limiting value we have to write. So limiting value is what? Mu n. If suppose mu is also given, okay, take like this is mu here. So what do you do? What is the normal contact force here? NB. So NA will come out to be mu NB, and NB is that. So NA value is mu m plus 1 G. Okay, now what more we can do? Now we have to talk about its rotational equilibrium. So rotational equilibrium. Now where to take torque? Any point you can take A, you can take B, you can take wherever you want you can take. I'll prefer B. Why? Because on B there are two forces acting. NB is also acting at B and friction force is also acting at B. So I'll prefer B point. You'll ask why B then? It is because the torque of NB also will be 0 about B and friction force also will be 0 about B. So torque of two forces became 0 because both are acting at that point. Torque of NB is 0 because where is R? Same way, force of friction also 0 because R is not there. So always prefer that point where more forces are acting. Okay, so what you will do? Sigma of torque about B is equal to 0. Okay, let's do. So mg is acting like this. This is mg. Okay, one more point in this one is required because this rod is in this position which is inclined. So angle also required. So let's assume that this is theta. Okay. Now let's solve. So mg is acting like this, and this is the point about which we are taking the torque. So mg into perpendicular distance I require this one. How much is this? This is L by 2. So this will be what? L by 2 cos theta. Simple. Okay. Mg into L by 2 cos theta. Plus this 1g is also there. Where is 1g acting? That also I have not given you. So take that one also. How much shall we take this? 0.6 L shall we take? Because this is already 0.5. So 0.6 we have taken. Okay. So 1g into, now this is 0.6 L, but I don't require this, I require this. So what did this will be? 0.6 L cos theta. Just like, exactly like mg, this 1g is here. Okay. So 0.6 L cos theta equal to, okay, both forces are downwards, they are producing a torque so that the rod can come down. Rod can go into which torque? Clockwise rotation. This is their NA. NA is also producing torque. How it's trying to take it? This way. Okay. How these two are trying to take the rod? It's acting downwards. How it will go? In this way. How this is acting? Like this, horizontal. Okay. So what is the torque of NA? NA is acting like this. Now what is the perpendicular distance of NA from this point? This is the perpendicular distance. So NA into this. Now how much is this? This total is L. This is theta. This is L sine. So NA into L sine. That's all. NA value you have. We'll put in this one. First thing is LL cancelled. Now you put this value. These are the two equations. Okay, there are the three. 1, 2, 3. With the help of this, whatever unknowns they are asking, we can find. Either they'll ask you mu, or they'll ask you NA or NB, or they will ask you theta. Okay, so with this one, we can find whatever they are asking us. Hardly ask, rarely ask, but it's a concept, so I told you. This is on torque. Alright. Then what next is there? Okay. One more question we'll do. Okay, so here is one string, here is one string. Okay, and with this one rod is hanging like this. It's like this. Mass M, length L. Question says, this string we are cutting. We are cutting this string. Okay, we are cutting this string. Now, when we cut this string, obviously this will go down, right? So they ask us with what acceleration is going down. Find the acceleration of rod when one string is cut or snapped. Is it okay? Fine. Earlier, if suppose when this string is not cut, if I make it it's in equilibrium. Okay. What we can say? Say here, okay, here is tension T. Okay, T1 you say. Here is tension T2. And mg is acting down. Very, very simple. T1 plus T2 equal to mg. And then rotational equilibrium also we can find here. But what he says, this they are cutting. So what's going to happen? This is going to move down. Right? So now condition is like this. This is the rod. Okay. Here is tension T acting. Here is mg acting. And we know that this is going down. So first equation if I write, it is mg minus T equal to mass into acceleration. It's going down, and acceleration only we have to find. Whose acceleration is this? Which point's acceleration? Center of mass. The acceleration of this point. Okay, first equation. Then what else we can do? This is rotating. Yes, obviously. So torque is there. Whose torque? About which point? I am taking about this point. Let's say this point is O. Torque about this point. Who's creating torque about this point? Mg. Torque of mg is there. So mg into what? L by 2. This is perpendicular, you can see. Okay. So mg into L by 2 equal to what? I alpha. I alpha. Okay. And this is alpha here. Because of alpha, it's going down. That is the angular acceleration. I can we find? Yes. I is ml square by 3. So ml square by 3 into alpha. M and M gets cancelled. L and L gets cancelled. So alpha value we have. Yes. Sometimes they ask you only alpha value also. You should be able to find out alpha. Alpha is there. Okay. Now what? I require acceleration. And unless I have tension, I cannot find it, right? Something has to be done. Otherwise, how will we are going to get it? Okay. We got alpha. But tension is also unknown, acceleration is also unknown. What to do? Something has to be done. So what you'll do? We are going to find relation between this acceleration and alpha. Right? So if this is going with angular acceleration alpha, then what will be the acceleration of this point? Is it in pure rotation about this? Yes. Yes. So what will be acceleration of this? I can say acceleration has to be r alpha. What is r? L by 2. This is L by 2. Okay. So this will be L by 2 alpha. A equal to L by 2 alpha. Alpha I already have. That means L by 2 into 3G by 2L. That's it. Yes. So we got 3G by 4. So acceleration came. Acceleration also came. Now they could have asked tension also from you. So if tension is asked, now this acceleration I am going to put in this one. Okay. So see then what's going to come. So mg minus t equal to m into 3g by 4. So t is equal to mg by 4. T equal to mg by 2. Okay, so if string is cut, this kind of questions can be asked from you and easily you can solve. If you know how to solve it, very easily answer will come. Okay, right? Then relation between torque and angular momentum. We already know that relation. Relation between torque and angular momentum. We discussed it yesterday. What is that? Torque is dl by dt. And I told you if external torque is 0, then what will happen? Say dl is 0. dl is 0 means angular momentum is constant. Angular momentum is constant. So now we are going to talk about conservation of angular momentum. Angular momentum is constant means if external torque is not acting, angular momentum is conserved, or conservation of angular momentum. Now in this one, what question can be asked from us? There are certain theoretical questions. What theoretical question is there? They will say that because of, let's say, global warming, okay, ice, where is ice? On the poles, South Pole and North Pole. We know that it is total ice is there. Okay, so if that ice is going to melt because of global warming, what will happen to the duration of the day? Okay, question is, if ice at poles melts, then what will happen to duration of the day? Duration of the day. Okay. So what you know now? This is Earth. Okay. Where is ice here? Here is ice. This portion if I make. Okay. Here is ice. Okay. Here also. There is ice like this. And this is the axis about which our Earth is rotating. Okay. Earth is rotating like this. So when we are saying that this ice is going to melt, where it will go? First of all, ice melts, becomes water. Water it becomes, that means it can flow. It can flow. So where it will go? It will go towards the center. Why? Because there is gravitation force acting on it. Gravitation forces. This is the center of the Earth. From here, gravitation force is coming. Okay. So if suppose I take one particle over here and it's free to move, this is how gravitation force is acting on that one. So what will happen? There will be two forces on that, two components on this one, right? One component, which direction? One component will be downwards in this way. Correct or not? One component will be downwards, like this. And one component will be horizontal. The same way it will be here also. And at the same time, there is one more force on them. What is that? There is rotation. So because of rotation, there will be another force on them. Which force? Centrifugal will be acting on them. Where will be centrifugal force? Centrifugal force will take them away from the center. So if suppose this particle again I take here. Okay, where is the circle of this? This is moving in this circular motion. So on this one, where is centrifugal force? It will be acting like this. So if this becomes water, okay, so it will start flowing. So this water particle, so this water will come out where? Here. So because this is coming over here, so what has happened? moment of inertia of this mass, which is as ice over here, became water. So because of that, moment of inertia is increased, because moment of inertia is what? M into radius square, right? So radius square, here radius is increased for the same mass as compared to the radius here. So because of that, I is increased. So if I has increased, omega will decrease. That means initial is suppose I1 omega 1 initially at this position. Okay, finally I2 omega 2. Now what we are saying is I2 is greater than I1, because here mass is coming and moment of inertia has increased because radius is increased. So I2 greater than I1, that means I2 by I1. I2 by I1 is greater than 1. Correct? And from here we know that momentum is conserved, angular momentum is conserved. It means I1 omega 1 equal to I2 omega 2. Right? Initial angular momentum, final angular momentum. So I1 by I2 is what? I1 by I2 is equal to omega 2 by omega 1. Correct? Here what you got? Here you are saying I2 by I1 is greater than 1. So what is I2 by I1? Omega 1 by omega 2. It means omega 1 by omega 2 is greater than 1. Okay. What is omega? 2 pi by t. So 2 pi by t1 by 2 pi by t2 is greater than 1. That means t2 by t1 is greater than 1. Greater than 1. T2 is greater than T1. That means time period in the second case will be more than time period in first case. That means duration of the day in the second case will become more than duration of the day in first case. Okay, so if ice melts and comes over here, day will become bigger by more than 24 hours. Okay, the day will become bigger. Right? Any doubt in this one, students? Is it clear? Yes, students, please say yes or no. Okay, good. Okay, right. What more we can do in conservation of angular momentum? See then, if suppose one ring we have, this is a ring. The ring's mass you will say m, and about its center it's rotating with angular velocity omega, and this is its radius. Okay, it's doing its motion like this. Suddenly, on this ring, two small particles, okay, two small particles are placed like this. Their masses m and m. Okay, its own mass is there. Its own mass is m. Radius is r. The question is asked from us, what is omega 1? What is going to be omega 1 if these two particles are placed on the same ring like this? We say, okay, fine. No problem. Angular momentum is conserved. The reason is because no external force is applied on this. No external force, no external torque. Are they applying torque on this one? Externally? No. Nothing they applied. But okay, fine. So in this case, first of all, what is angular momentum? Say I omega. What is I? mr square. In the final case, what is angular momentum? Now in this one, there is moment of inertia of ring also plus their moment of inertia we have to add. So mr square plus 2mr square. Okay, its moment of inertia is what? mr square. Its moment of inertia also mr square. We add it along with ring. Ring's moment of inertia, we were knowing mr square. We added. This is omega 1. Then L1 equal to L2. That's all. L1 equal to L2. So mr square into omega equal to r square m plus 2m into omega 1, r square cancelled. We have got m by m plus 2m into omega. That's omega 1 value. Okay, no problem in that. Then what else we can do in the conservation of angular momentum? These are the questions. Okay, now more examples are what? People say that the dancer, skate dancer. Okay, what she'll be doing? She'll be changing the position of her hands when she stretches her hands. So what she do? Moment of inertia increases. Moment of inertia increases, its omega decreases. Okay, whenever she folds her hand, suddenly she will be gyrating faster. Omega will increase. Reason? Because moment of inertia is decreased. Moment of inertia is decreased and angular momentum is conserved. So whenever you increase moment of inertia, omega will decrease. Whenever you decrease moment of inertia, omega will increase. Okay, that's how skate dancers and swimming divers will be diving. Whenever they have to turn, okay, what they will do is they fold their body. So they will make turns. When they have to be straight, then they will stretch their body. So then they will go straight. Okay, so that's how conservation of angular momentum questions will be asked from you. Okay, now then what next we have? Now I am taking one question in which collision I will apply. Okay, collision is here. So how we'll do? Suppose I have a rod. Okay, and this is hinged here. Length is L. Its length is L. And mass is M. Here one bullet is there. Its mass is M. And its speed is u. Okay, this goes and strike this bullet, hits the rod at the bottom and sticks with it. Sticks with it means which type of collision? We can say inelastic collision. Sticks with it. Okay, then what he wants? Find an angular velocity of the rod, or find angular velocity of rod plus bullet system. Okay, find angular velocity of rod bullet system. Okay, so this is the question. Just a moment. Right. Okay. So what you can do here? So this goes and hits it. So there is a collision happening. Okay, and this sticks with the rod. So if I see just before collision and just after collision. Okay. First thing is we have to decide what we are saying as a system. So in the question itself given the rod plus bullet system. So that means we have to consider bullet and rod both. So before collision also you have to consider both. After collision also you have to consider both. It's not possible that after collision you take rod and bullet, but before I'll only talk about rod. That's not possible. Okay, so system is rod plus bullet for us. Fine. Now what are we trying to do? I am going to conserve angular momentum about point O. This is suspension point. Here I want to conserve angular momentum. So the question is there any external torque acting? During collision is no external torque acting on that. So see now, during collision what is happening? This is rod, bottommost point of the rod is this, and here is bullet. What happens? Bullet applies the normal contact force during the collision on the rod like this. Okay. Same way rod applies the normal contact force on the bullet. So if these two are system, then where is the net force? Net force is 0. So torque about this point also will become 0. Correct or not? So I can conserve angular momentum. That's no problem. So I am going to conserve angular momentum about point of suspension. Conserving angular momentum about point of suspension. So first is L initial. L initial means who is moving? Only bullet. So angular momentum about this is what? Linear momentum into perpendicular distance. Okay, perpendicular distance of what? From point of suspension to the direction of momentum. So mv or mu into L. That's all? Yes, because rod is at rest. So initial angular momentum MUL. Now finally, this particle sticks here. Now this is going to move with omega. So now I of the system, because now it's a rigid body totally. So I of the system into omega. Now I of system is what? I of system is I of rod plus I of bullet. So I of rod means ml square by 3, right? About one end only. So ml square by 3 plus for this particle ml square. The single particle about this moment of inertia ml square. So this I am going to write over here. L square you can take common. Then what do you have? M by 3 plus m. M by 3 plus m into omega. Now Li equal to Lf. That's it, over. Okay, so omega equal to what? L and L will cancel. So omega is mu by L into m by 3 plus m. That's omega value. Okay, so this type you can do with collision also. If collision is coming, even then we can find omega with the help of conservation of angular momentum. Like what we did in conservation of momentum. There also collision was there. Here also collision is there. Okay, so in collision also we can apply conservation of angular momentum. Okay. Now what? Torque we have seen, angular momentum we have seen. Now energy, kinetic energy. Kinetic energy. Okay. But kinetic energy of what we are saying here? Kinetic energy of rotation, kinetic energy of translation. Both we are going to see because we are going to enter into rolling, right? So first is kinetic energy of translation, we all know. Half mv square. And kinetic energy of rotation, pure rotation, is half I omega square. Half mv square, half I omega square. If it's in rolling, which we are going to see now, okay. So in rolling what happens? Body rotates also and translates also. So in that case, kinetic energy becomes kinetic energy of translation also and kinetic energy of rotation also. So that means it will be half mv square plus half I omega square. Okay, let's solve one question. Work energy theorem. We will solve a question on work energy theorem here. Okay, what is work energy theorem? See. Suppose this is ground. We have one rod here. Okay, we have one rod. Now we are saying that this rod is actually going down. Okay, Let's make this a suspension point here. That means this is not going to move anywhere, and this rod will come down. Okay. So question asked from us is, when this rod is going to touch the ground, what will be its angular velocity? With what angular velocity this is going to touch the ground? Okay. Mass is m, length is l. Okay. Question is, find angular velocity of the rod when it strikes the ground. When it strikes the ground. Okay. Now the question is, why it should come down? Maybe slight disturbance is there in this direction, that's why it came down. Fine. How we are going to solve? Work energy theorem. So which force is working here? Gravitation force is working. Because if you talk about mg is acting here. Gravitation force is here. And you see that now where is mg? Here. So there is motion of that or not? It has displaced the object or not? Center of mass has come down or not? So that means gravitation force has worked. So work energy theorem will be using, or you can use conservation of energy also, because only conservative force is working. Okay. So work energy theorem the work done by gravitation force equal to change in kinetic energy. Okay, conservation of energy also we use. Potential energy initially, kinetic energy initially, potential energy final, kinetic energy final. Same thing here also. So work done by gravitation. Now gravitation force is acting down and displacement is also down only. How much is the displacement? L by 2. L by 2. Vertically acting, so vertical displacement. Don't take this displacement. Then in that case, if you are taking this component of mg also you have to take. Okay. Forget it. Okay. Mg is acting down, so displacement is L by 2. So mg into L by 2 equal to what? Half I omega square. Initial kinetic energy is 0. Final kinetic energy is half I omega square. Okay. So mg L by 2 equal to half ml square by 3 into omega square. So m and L you can cancel. 2 and 2 also cancel. Omega is what? Root 3g by L. Omega is root 3g by L. Okay. So if rod is coming down, angular velocity will be this. But at the same time, suppose they ask you what is its velocity. Find velocity of center of mass when it strikes the ground. So no issues. Velocity of center of mass. This is L by 2. And is it in pure rotation? Yes, because this point is fixed. It's in pure rotation. So we can say that velocity of center of mass will be L by 2 omega. So multiply L by 2 into root 3g by L. Okay, this is the answer. L we can, what we can write? 3gl by 4. Okay, this will go inside and become L square, right? L and L gets cancelled, so root 3gl, and this will go inside, so 4. This will be the answer, right? Okay. Now what then? Now we are going for rolling. Rolling in which type of bodies we talk? We talk about circular bodies. Ring, disc, spheres, cylinders. We can talk about rolling. Okay, rolling means what? Translation plus rotation. Translation plus rotation. So, if we see them separately first, we say only translation here. Okay, and only rotation we are going to talk about here. So only translation. Translation means is all the points of this particular body will be moving with same velocity. That's translation. Means normally how we saw a sliding motion. Okay, how we considered sliding motion in laws of motion when we were studying. The entire body, entire object was moving together with acceleration A or velocity V. Right? Exactly same way. So this is translation here. Pure translation. So center of mass is moving with V, topmost point is moving with V, bottom point is moving with V, this point is also moving with V, this point is also moving with V. All the points have the same speed. This is translation. Pure rotation. What is this? This isn't pure rotation. It's omega. Okay, so what is the velocity of the topmost point here? Topmost point's velocity is r omega. Where? Direction, you see that. Rotation is like this. So topmost point is where? Here. Like this. R omega. Bottom. Bottom means like this. Where it is going? Back. Here. Like this. So r omega. This point. Up. R omega. This point. Down. R omega. Pure translation, pure rotation. You are mixing them up. You are calling it as rolling. So what's going to happen? If you are calling it as rolling, then this is rolling here. So topmost point's velocity is what? V plus r omega. Okay. And center point is moving with V. Because center point due to this one. No, well, r is not there. No, center point, r omega. All the points on this one will have what velocity? R omega. R is 0. So what will be the velocity of the centermost point? 0. So centermost point in rolling will be moving with translation velocity V only. Okay. Topmost point velocity V plus R omega. So V plus R omega. Bottom, this is V, this is R omega. So bottom point V minus R omega. Okay, this point V in this direction, R omega is in upward direction. V is here, R omega is here. That means what will be the direction of this point? Like this it will go. Resultant. This point is here, let's say. V is in this way, R omega downwards. So what will be the direction in which this will be going? Like this. So every point in rolling will have different velocities, and certain times they ask you this only. What is the velocity at the top? What is the velocity at the bottom? What is the velocity here? What is the velocity there? That is also the question they ask. You should be able to find. Okay, you should be able to find. Now this is rolling. Now let's talk about pure rolling. What is the meaning of pure rolling now? Pure rolling means is no slipping anywhere. Okay, there is no slipping. Means if this is a rolling body and we are keeping it on the ground. Okay, we are keeping it on the ground here. Right, it's in rolling. We are saying it's in rolling. That means rotation is also there and translation is also there. This is V, this is omega. So here is the contact. This point, if it is having speed V minus R omega, as you said in the previous, the bottommost point is moving with what speed? You see? V minus R omega. So, if it is having velocity, that means this is going to slide on the bottommost, rather on the surface. If this point is having any velocity, bottommost point has to skid on the ground, no? Correct or not? So then this will slip. So in which case it will not slip? When this velocity is 0. Only in one case you are not going to slide. If suppose my hands are in contact and if my hand is moving above hand, so obviously it is sliding on my below hand. When there will be no sliding? When they are at rest. If they move, there will be sliding. So exactly same way. If suppose this point is having any velocity, it will slide. So in which case there will be no slipping? When this is at rest. Okay. So for no slipping, V minus R omega need to be 0. That means V should be equal to R omega. What is V? Velocity of center of mass. R omega. This is the condition of no slipping, and this is only for pure rolling. Okay, so if it's in pure rolling, now what will be the velocity of all the points? That you'll see. Okay. Okay. Now we are going to find velocity of all the points. So velocity of bottommost point is what? 0. We know now because this is pure rolling. Okay. Its velocity here 0. Center point V. Topmost point. Topmost point, what was the velocity? V plus R omega. But you already said that V equal to R omega. V plus R omega becomes what? 2V. Velocity of this here. What is velocity of this? Let's go back and check. V here, R omega here. But we are saying R omega is also equal to V. So this is also V, this is also V. So what will be this? Root 2V, because they are perpendicular. Okay. So root 2V will come. Direction. And what about this point? This point also, V forward, R omega downwards. So velocity is direction this, root 2V. You should be able to find the velocities. They can ask you, what about this point? V in this direction plus, this will be maybe radius is x, then V plus x omega. Here is V plus R omega, here will be V plus x omega. This point, V minus x omega. That's what I'm saying. You should be able to find the velocity of any point because there are questions on that. Same way acceleration also. The acceleration of center of mass is a and angular acceleration is alpha. So here will be a plus r alpha, here will be a minus r alpha. Here will be a in this direction, r alpha upwards. Here will be a in this direction, r alpha downwards. So if they are asking you acceleration also, same way you can do acceleration also. In place of omega you write alpha, in place of v you put a and solve it in the same way. Okay, so this is pure rolling. Alright. Okay, then kinetic energy in pure rolling. Kinetic energy in pure rolling. Now we know that there is translation also, there is and there is rotation also, and it's in pure rolling. Then we know that V is equal to R omega. Also, we should be able to write. Okay, so kinetic energy of rolling. What you'll do? We are writing half mv square, which is because of translation, and half I omega square, which is because of rotation. Okay, fine. This is half mv square as it is, no change. Whereas this is half I omega square. Now how should we write? Because it depends on different system. Rings different, solid sphere is different, disk is different, hollow sphere is different. So what shall we write I? So what I'm going to write I is mk square. I'm writing mk square. Now k is what here? What is k? K is radius of gyration. Okay. What is k? Radius of gyration. We'll discuss it. Okay. So this K is radius of gyration. Omega is what? Omega we can write V by R. So V by R whole square. So what we are getting? Half mv square plus half mk square v square by r square. So take half mv square common. Then what we have? 1 plus k square by r square. Okay, 1 plus k square by r square. Now this 1 plus k square by r square, in certain places they call it as beta. Okay, what it is, I'll tell you that, but at the moment I am writing it half mv square into beta. What is this beta? Beta is 1 plus k square by r square. Okay, now what beta is from here? This is kinetic energy of rolling. And this is what kinetic energy of translation. So beta actually is, we'll write with a different color. Let's write here. So beta is kinetic energy of rolling by kinetic energy of translation. Okay, kinetic energy of rolling by kinetic energy of translation is beta value. Clear? Now, the general relation. Sometimes when they ask you kinetic energy of rolling by kinetic energy of translation, they are asking you beta. Directly you can say 1 plus k square by r square. You don't have to calculate anything. But before that, what is k? What is radius of gyration? Okay, let's discuss what radius of gyration is. Radius of gyration. Okay, now radius of gyration basically tell us that what is the distance between two axes of rotation that we are going to consider. What is the meaning? Now suppose I take ring, not ring, I'll take disc. Okay, there is a disc here. So we made a disc. Okay, this is our disc here. Now we know that moment of inertia of this disc about an axis which is passing through center perpendicular to plane. Okay, what it is? mr square by 2. Okay, now radius of gyration says if this moment of inertia I am going to write as mk square. If I write this moment of inertia as mk square and I equate it with mr square by 2, m and m gets cancelled. So k value is coming r by root. What this is? This we call as radius of gyration. It means another axis which is at this distance from this one, maybe here. Okay, which is here at distance k. Okay, so about this axis, I'll be saying that moment of inertia is mk square, where k represents the distance between these two axes. Okay, this is radius of gyration. So can we calculate this radius of gyration for anything and everything? Yes, we can. If suppose I am talking about sphere, and sphere's radius of gyration we have to find. Okay, so sphere is what? A sphere's moment of inertia is 2 by 5 mr square. Now its radius of gyration I want. So this I immediately I'll write mk square. Okay, whenever you are using radius of gyration, moment of inertia will be mk square, where k is radius of gyration. Okay, so this is also equal to 2 by 5 mr square. So k value is what? Root 2 by 5 r. Hollow, this will become 2 by 3. So root 2 by 3 r. Can we apply this in any body, any object? We can apply. This is basically a concept in which you are finding out the distance, another axis. from already known axis, where we can say the moment of inertia of the body is mk square. You can generalize it. Whatever the body is there, we can say that okay, its moment of inertia is mk square. K will be different, and that K is called radius of gyration. How to calculate radius of gyration? Just equate the moment of inertia about known axis with mk square. Then K will be giving you the distance of another axis from known axis. Okay, where we can say moment of inertia is mk square. That's all. That's radius of gyration. Okay, so this is how we calculate radius of gyration. Let's come back. 1 plus k square by r square. So what is this beta value for different bodies that we have? For ring, what is its value? For disk, what is its value? Let's see. So beta for ring. Okay, what is it? 1 plus k square by r square. Now in ring's case, what is there? What is moment of inertia? Mr square. From the center, moment of inertia is mr square. So mr square equal to mk square. That means k equal to r only. Okay, so 1 plus r square by r square. Beta value is 2 for ring. For disk already we calculated k value, right? What is k value for disk? R by root. Okay, let's place it. 1 plus r by root 2 whole square by r square. Okay, r square cancelled, 1 plus 1 by 2, that's 3 by 2. Okay, beta for solid sphere. What is it? What is k value for solid sphere? Let's see what we have done. Root 2 by 5r. Okay, so 1 plus k square, so root 2 by 5 r whole square by r square. So what we are getting? 1 plus 2 by 5, that's 7 by 5. Okay, beta for hollow sphere. For hollow sphere, what it will become? Let's see. If I am going to have here hollow sphere, then we will write I equal to 2 by 3 mr square. So mk square equal to 2 by 3 mr square. M gets cancelled. K value root 2 by 3r. So place it here. 1 plus root 2 by 3r whole square by r square. So 1 plus 2 by 3, that is 5 by 3. So beta value is different for different objects. What this beta is going to do? Wait and see. Okay, it is going to make our problems little smaller to solve. It is not that it is going to make something different, but we will get the answer quickly. What beta is actually? Kinetic energy of rolling by kinetic energy of translation. You got it from here. Clear? Sometimes they ask you direct beta. I told you this is the relation. Translation to total rolling. Okay, relation of kinetic energy. The ratio they ask. Kinetic energy of translation by kinetic energy of rolling, or rolling by translation. Rotation by translation. Anything they can ask. Okay. Fine. Let's see now. So now most common question that we solve actually in rolling, you'll find it everywhere. That is when these bodies are going to slide down an inclined plane. So here we'll make one small ball. Okay. This ball can represent ring, can represent disc, can represent solid sphere, can represent hollow sphere. Okay. We're going to move down. Okay, see, one by one we will solve and see what's coming and how beta is going to help us. Okay. Right. What is going to happen? Pure rolling is going to happen. Okay. How pure rolling is going to happen? Mg sin theta is acting over here. Mg sin theta is going to make it accelerate. And who is there to give it angular acceleration, because mg sine theta cannot give angular acceleration because it's acting at center of mass. If a force is acting at center of mass, it cannot rotate the body about center of mass. Not possible. So you require some other force. And what is that? Friction. Friction is acting like this. And friction is making it move in this way. So is friction necessary? Yes. If you are applying the force on the body, then friction is necessary to make it rotate. If the force is at the center, then it cannot rotate. So somebody is required to rotate. Friction will do that. Alright. So if I have to find its acceleration of rolling body, what we will write? Let's say that okay, acceleration of rolling body is A. First equation, if I am writing, it will be mg sine theta minus friction equal to ma. Mg sine theta minus friction equal to ma. Second one, who is rotating it? Friction. So force of friction into R, that is the torque. Force of friction is applying about center. The force of friction into R equal to I alpha. I am not writing at the moment because I am saying I am representing it everything, disk, ring, this, solid sphere, hollow sphere. So I am writing as mk square. Okay. Force of friction into R equal to mk square into alpha. Why mk square? Because mk square is moment of inertia of everybody, everything. K is different, but generalized form is mk square. So force of friction into R equal to mk square into alpha. And I told you this is in pure rolling. So pure rolling, which pure rolling this is? This is called accelerated pure rolling. Accelerated pure rolling. Now condition for accelerated pure rolling is what? A equal to R alpha. Like what it was V equal to R omega when we are not talking about acceleration. Here it is A equal to R alpha. So alpha value I can write as A by R then. So that means force of friction is mk square A by R square. Correct? Now this force of friction I am going to put it over. So mg sine theta equal to ma plus mk square A by R square. Take A common. In fact, ma is common, not A common. Ma is common. 1 plus k square by R square. And this is mg sine theta. Gets cancelled. Acceleration is g sine theta by 1 plus k square by R square. So this 1 plus k square by R square is something known. Just go back and check what is this. Oh, that's only beta. 1 plus k square by R square is only beta. So that means acceleration here is, what is g sine theta? G sine theta is tangential acceleration due to gravitation, right or not? Not tangential, translation, because of the force. Which force? Which is acting at the center. So what acceleration it was giving? G sine theta. So can I remember it like this? G sine theta by beta. Acceleration is g sine theta by beta. Okay, g sine theta by beta. In pure rolling, acceleration of this is going to be g sine theta by beta. Okay, fine. So this will become smaller for us. This much I will not calculate. Okay. What about its velocity? I want to know what is the velocity of this one when it is reaching at the bottom. Here. What's going to be its velocity? Okay, what velocity? This velocity. Center of mass velocity. That's velocity of rolling. What is it? Said okay, fine. No problem. Now it's in pure rolling. The question is this point sliding over here? Answer is no. It's not going to slide. Okay, fine. So now, if I want to find its velocity over here, shall we conserve energy? Why not? We can conserve energy. Or we can use equation of kinematics also to find out the velocity of translation. And from velocity of translation, we can find velocity of rolling also. That also we can do. Okay, so let's do. Whichever way we want to do, we can do. Okay, so conservation of energy shall we do? But friction is acting. Can we still conserve energy? Yes, because work done by friction is zero. This point is not sliding. So if this point is not sliding, work done by friction is zero. Okay. So conservation of energy if we use, then what is it saying? Kinetic energy initially plus potential energy initial equal to kinetic energy final plus potential energy final. Okay. So kinetic energy initial here, say 0. Potential energy initial. So what he'll do is, shall we take H? Height we have to take. This is H. Okay. So potential energy is mgh. Kinetic energy final. What shall we write? Because we have to write rolling kinetic energy. So rolling kinetic energy half mv square into beta. Check. Okay. So half mv square into beta. And potential energy final 0. So what we have got? Mgh equal to half mv square into beta. M gets cancelled. This is 2gh by beta is V roll. Normally, if you would have talked about just a sliding one thing is there which is going to slide on this one. What will be its velocity at the bottom? It's a root 2gh. We know that. But since we are talking about rolling here, what we are talking? Root 2gh by beta. Here what we talk about? G sin theta by beta. Here we are talking about root 2gh by beta. So beta is helping. Time, let's say time of descent now. How much time it takes to come over here? Okay. So in that one also beta will be there. Let's see. Let's see if beta is coming or not coming. So time of descent. Time of descent. Okay. So now this much distance it is falling. This is h. This is theta. So sin theta equal to h by this. So this will come as h by sin theta. Okay. This distance is h by sin theta. Acceleration I know, distance I know. I can use equation of kinematics. Okay, s equal to ut plus half a t square. So h by sin theta, initial velocity 0 plus half a. Acceleration do I have? Yeah, acceleration is there. Where it is? Acceleration. Where we have? Yeah, this is here. G sin theta by beta. So half g sin theta by beta into t square. So what we are getting? See then. T square I want, so h by sin theta equal to half g sin theta by beta into t square. So this goes 2h beta by g sin square theta equal to t square. What is final formula for time of descent? Just removing this from here. A time of descent formula is 1 by sin square theta or 1 by sin theta root over 2h by g by beta. Okay, normally time of flight, time of descent root 2h by g. Correct or not? But here h is what? H is h by sin theta. H by sin theta. So sin theta is here. But here it is what? normally translation, how much used to be the time of descent? 2h by g. So here root 2h by g by beta. So for everything you see, acceleration also, whatever is translatory acceleration by beta. Velocity also, whatever velocity root 2gh we used to have, so root 2gh by beta. Time, root 2h by g, so root 2hg by beta. So everywhere this beta is coming. So if we remember this way, we can minimize. Okay, in rolling, this much is time. In rolling, this much is acceleration. In rolling, this much is velocity. Okay, this will help us in reducing the time for calculation. Right? So time of descent we saw, velocity also we saw, acceleration also we saw. Now let's find out if this is disk or ring or solid sphere or hollow sphere, which is going to take least time to reach the bottom, which is going to, whose acceleration is more, whose velocity is more, everything. Okay, let's find out. So this all I am just removing. This is all not required, only the relations. The relations are important, final relations. Okay, so acceleration is here, time is there, velocity is there. So acceleration first. If it's a ring, okay, in ring's case, what is beta value? We calculated. For ring, beta is 2. Okay, so let's see what is the answer. Acceleration of ring, g sine theta by 2. For disk, its value is 3 by 2. G sine theta by 3 to 2. Solid sphere, it came out to be 7 by 5. So 2g sine theta into 7, and here is 5. Okay, I am correct. Let's check. Yes, 7 by 5, and this one 5 by 3. Okay, let's do acceleration of hollow sphere. So g sine theta by 5 by 3. So whose acceleration is maximum? You can see that this is g sine theta by 2. That means 0.5 g sine theta. It's 2 by 3, 0.66 g sine theta. 7 by 5, this is 10 by 7. 10 by 7 means it's more than 1. How much? I think 1.4 g sine theta. And this is 0.6 g sine theta. So who's fastest? Solid sphere. Solid sphere's acceleration is maximum. Then disk. Then hollow sphere. Then ring. What about velocity? Same thing actually. Because here also beta is in denominator. Here also beta was in denominator. Where? Here. Right? So beta is in denominator here. So whose velocity will be more? Whose beta is least? Okay. Whose beta is least? This is 2, this is 3 by 2, this is 3 by 2 means 1.5. This is 7 by 5, 1.4, and this is 5 by 3, 1.66. The least is for this. So velocity also for solid sphere will be maximum. Acceleration also for solid sphere, velocity also for solid sphere. Then time for solid sphere should be minimum. Time for solid sphere should be minimum. Why? Because beta actually will come at the top. Beta, its relation was what? Because this is root 2h by g by beta. So beta will go at the top. It was actually like this. Root over 2h beta by g. So whose beta is minimum? Solid sphere. So time will be minimum for solid sphere. So who will reach fast? Solid sphere will reach fast. Who will reach the latest? Ring. All are related to beta. So if we remember this kind of a thing, then we can solve certain things easily. We are not going to solve it for every question. Okay. Okay. Then, other than this, any more questions are there that can be asked from us? Yes, obviously. I suppose that there is a ball, hollow sphere you can take. Oh, this is the rough surface. Coefficient of friction, we can say mu is there. Okay, I have given velocity to the ball. No rotation, only velocity we have given to the ball. And we are asking when it will start pure rolling, after what time, and what will be its velocity at that time. Okay, find when will it start pure rolling and what will be velocity then. What will be velocity then? Okay, so one method is there, the conventional method. There will be friction will be acting that side, here friction will give it torque. Okay, so friction will give it alpha. All this we have to solve. Second one is smarter method. Smarter method is smaller method. What is that? That method says, we talk about this point here. Okay, friction is acting at this point, we know. True. But if I am going to talk about this point, and if I am going to talk about this point only, not about this point, talk about this point, then torque about this point is 0. Because friction is acting at that point, it can't produce the torque. So, at this point, is there any other torque acting? No. If suppose this point I say is point P. So, torque at point P is not there, is 0. 0 it is. Okay, fine. So, if I say I am going to conserve angular momentum about this point, whatever at the moment we know I know that it's not in pure rolling, but after some time it will be in pure rolling. Correct or not? So, after some time when it will be pure rolling, then also angular momentum about this point will be conserved only. It's not going to change. Right? Okay. So, that way we should be able to solve. So, what do you say? Conserving angular momentum about point P. That is it. Now what? After some time it's going to pure roll, I know. So suppose it's going to pure roll somewhere here. And then its velocity has become V1. And it has also got omega, which is, let's say, omega 1. Okay. Velocity is V1 and angular velocity is omega 1. Correct? So now you see. Initially, what is its angular momentum about point P? So what type of motion this is having? Only V. Linear motion, no angular motion. So about this point, this distance is R. So what is its linear moment, rather angular momentum? I say MVR. That's all. MVR. Initial angular moment. Final. Now finally, it's having omega also, it's having V also. So we'll write MV1R plus I omega plus I omega. Okay, now what we have taken, this is a ring or what it was? I have not written. So let's take it as disk. Let's say this is disk. Okay. So if it's a disk, then I know its moment of inertia will be mr square by 2 about the center. So mr square by 2 into omega. What is omega? V1 by R. Why? It's in pure rolling here. So V1 equal to R omega 1. It's in pure rolling. Okay. So what this is now? MV1R, this R and R gets cancelled. So MV1R plus MV1R by 2. That means 3 by 2 MV1R. MV1R. Now since we said angular momentum is conserved, conserving angular momentum, that means this and this are equal. Equate them. 3 by 2 MV1R equal to MVR. So M and R gets cancelled. So V1 is what? 2V by 3. I got velocity. What is the velocity of rolling? I got V1 is equal to 2V by 3. Now question was when it's going to start pure rolling. Okay. So here its velocity is V, here its velocity has become 2V by 3. Velocity has decreased. Who has done it? Friction. So can we get the time? Obviously we can get the time. Okay. So what do you do? Equation of kinematics I am going to use. Okay. So what is that? V equal to U plus AT we will use. What is V value? 2V by 3. What is initial velocity? V. What about acceleration? Who is giving acceleration? Friction. What friction is there? Kinetic friction, because initially it was sliding. Which friction is there? Kinetic friction. So force of friction is kinetic and its value is what? Mu n. That means mu mg, because n is upwards and mg is downwards acting here. Okay, mg is down and n is upwards. So force of friction is mu mg. So how much retardation it will give? And force of friction equal to mass into acceleration. So mu mg equal to ma. So acceleration is what? Mu g. Put it here. Acceleration is this or retardation? Retardation. That's all. So 2v minus 3, 2v by 3 minus v. Minus v by 3 minus mu g into t. What is t value? V by 3 mu g. That's it. Finished. First we found velocity by conserving angular momentum and then we found time. Easy. Okay. Now use of this one more time we'll do. But I am going to frame the question in different way. See. This is clear? Any doubts, students? Students, any doubt? Yes, students. What happened? Okay. So last question for today. What are we going to do? Collision I am going to apply in this now. How to apply collision? Suppose this is ground, okay, and I am going to have a wall here. Same ring only I am doing, okay. It's not ring, disc. This is the disc having velocity v, having omega. It's in pure rolling. It's pure rolling. And this surface, this is rough surface. Friction is there. So since it's in pure rolling, obviously this point is not sliding. So no problem. Keep on rolling. But here I am saying that collision is happening. Collision is elastic. Okay. So I'll just explain you what's happening first, okay? Then we'll frame the question. Sorry. Okay. So this ball here reached, okay, collided with the wall. Then what happens? Elastic collision is this. So center velocity will be changing. It becomes velocity in this direction. Question is, what about omega? Omega will remain same. Omega is still like this. Omega is still like this. Okay. Question is why? Why like that? The reason is because when the wall collides with it, wall apply normal contact force on the ball in this direction, because of which its momentum change, linear momentum. But there is no force in this direction which can provide torque so that this omega can change. So that's why omega remains same. So now how this kind of motion is there, you see that what will be the velocity of this bottommost point in this case, it is here, v plus r omega. So this point is going to slide here. So friction is going to act. Friction will be acting on this backwards. So in this case, if they ask you, what will be the final velocity when it will start pure rolling after collision or time, how to do that? Method is same, concept is same. I am going to take this point over here and I will say that angular momentum about that point is conserved. Okay, angular momentum of this point is conserved. So first is how to write initial angular momentum. That is only important. Final you already know. We written in the previous question. Same we'll write. Initial angular momentum. So what I will be writing? Minus MVR. Why? Because in this direction I am taking. Minus, or you want to write plus. One thing we have to write minus, we have to write another thing in plus. Why? Because about this point velocity is in this direction. So okay. So how is the angular momentum? Direction is towards you. Whereas omega is like this. So it will be in other direction. So one positive, one negative will come. So okay, first you write this as positives and then that will be negative. So minus I omega. What is I? Mr square by 2 into omega. But omega is V by R because you are saying here it's pure rolling. Okay, omega is V by R. So write it. This is initial. Final it's in pure rolling again. Vm V1R plus Mr square by 2 into V1 by R. Okay, so this we already know. 3 by 2 MV1R. And pure rolling. Okay, but here what it is? Here it is half. Now equate that. What will be V value? V1 value. V1 value will be V by 3. Same question, only two lines initially in the question they have added. This is going and colliding, and after colliding, when it will start pure rolling. Clear? So that's all. This is it. So rotation is over. Okay. Tomorrow we are going to start gravitation. But today I will be posting practice test for this one. Alright students. So go through it. All the concepts we have covered up. Nothing is left. Solve all the questions that we have done and practice test so that you can get the confidence. Okay. Alright then. See you tomorrow. Bye bye.